this chapter, we will be looking at various types of functions. In this lesson, we will be looking at the products and quotients of functions.
Okay, well, you had to know that if we at one point look at adding and subtracting functions, we're going to end up looking at multiplying and dividing functions. And that's what we're going to do right now. So just pay attention to some of the notation here. H of x, if that's equal to f of x times g of x, one way of writing it is to use a solid dot in between the two. So f dot g, okay? But you should probably at this point be familiar with the use of the dot for multiplication. The reason I'm highlighting it right here is because in a little bit here you're going to see a bit of an altered notation here, and it means something different. You're going to see an open circle. That means something very different than multiplication. So closed circle here means multiplied by. Okay, and when it comes to the quotient, there's really nothing we can hide here, no special notation. F of x divided by g of x, or f divided by g all of x. Okay, now the domain of the product of the functions is the domain, once again, common to the original functions. You can't multiply functions together where they don't exist. So it's got to be common to both those functions here. However, the domain of the quotient, and this is the interesting one here, right? The domain of the quotient, you got to take into account that division by 0 is undefined. So it's not going to be necessarily the whole domain of the denominator, okay? There's going to be issues here. So wherever the domain goes to 0, that is a restriction on x, and so that's what we're getting over here. The domain of the quotient here is further restricted by the values of x where that denominator goes to 0. Can't have that. But as we've seen, we already have an idea of what that means. That could be a vertical asymptote if it's what we call an essential discontinuity, if it's something you can't get rid of. Or it could be a hole in the graph if it turns out that the factor in g of x that goes to 0 is shared by the numerator. Okay? And then finally, this last little bit here, the range can be determined by inspecting the graph of the product of the quotient of the functions. Essentially, the range kind of works like the outcome of an experiment. I really shouldn't know what the range is before I apply, or before I actually graph the functions or go through the process of figuring out what they look like. That's the whole point. Okay, the y values are these unknowns to me. They're the responding variable, okay, the dependent variable. Depends on what I use for x. So we can just graph it and have a look. So now we're just going to run through some questions that basically mirror what we did with adding and subtracting. We're just now going to look at it in terms of multiplication and division.
If f of x is equal to x plus 2 and g of x is equal to 2x minus 3, determine h of x, which is equal to f times g of x, and graph it to determine the following.
All right, so let's just jump right in here and inspect for ourselves what the domain and range are of the constituent functions and then the product here. So we've got f of x is x plus 2, g of x is 2x minus 3. We're going to multiply those together, okay? Let's just do that right now. Let's go through do the process of multiplying them so we know what we're looking at here. H of x is going to be x plus 2, and g of x is going to be 2x minus 3. Multiply that, we're going to get 2x squared. What do we got here? Minus 3x plus 4x, so plus x minus 6. All right. Now, the domain of my f of x, which is just x plus 2, and x plus 2 is just a linear function. That's going to be x is an element of the reals. It's a linear function with a slope of 1. My range is going to be y is an element of the reals. Okay. G of x is a linear function, 2x minus 3. That is going to have a domain that's an element of the reals. Its range, again, because it's just a line with a slope of 2, y-intercept of negative 3, it's going to be all reals. Now, the domain of h of x, because the domains of both of those are all reals, the domain of h of x is going to mimic that. It's going to be all reals. However, the range isn't going to be. This is now a quadratic. And what I might do here is complete the square to figure out what the vertex is going to be. So take out the 2 here, x squared plus 1/2 x. Okay, now I'm going to move that negative 6 out of the way here. And then half of this is going to be 1/4 squared. So I'm going to add 1/16 minus 1/16. Okay, take out the negative 1/16. So 2 times x squared plus 1/2 x plus 1/16. That's going to be minus, what do we got here? Minus 1/8 minus 6. And so finally I'm going to get 2 times x plus 1/4 squared. And what's this going to be? Negative 48, so minus 49/8. I hope that's what you get there. Let's just multiply numerator and denominator by 8 there, 48, yep. So my vertex here is going to be the point negative 1/4 comma negative 49/8. Okay, the domain, now this is a parabola that opens up. Okay, this is the vertex, which means the minimum value here, y is going to be greater than or equal to negative 49/8. So it's not quite so straightforward to get the range. Okay, the range is not going to necessarily mimic what we saw with the previous 2 functions. I kind of got to treat that as its own little thing there and work it out on my own here. But thankfully I have enough experience, okay, with the linear functions and then the quadratic functions that we can figure out what the range is supposed to be. Or you could answer the question like it asks you to answer it, and you're supposed to graph it to determine the following here. So what I'm going to do here is, okay, if we graph, for example, in this case, x plus 2, x plus 2, and then we've got 2x minus 3, x minus 3. If I graph these two right here, I will see, yeah, this is why I should always go to my zoom standard before I do anything with that. There's my first graph, there's my second graph. And you can see that you've got, there doesn't seem to be any significant breaks there, element of the reals here. Now, what I can do here to get the product of the two, actually I can press my vars button right here, go over to the y vars, okay, and then the only one here that I recognize is function. This is where I've stored my equations here. So I'm going to choose y1, okay, and I'm going to multiply that by, and again, I'm going to go into my vars, over to y vars, choose function, over to y2. So what this is going to do here is this is going to go up to the function in y1, to the function in y2, and multiply them together. Now, if I graph this, okay, I get this function right there, and that function represents the product of those two. I can find the minimum by going into my trace, my menu, my calc menu, choosing minimum. Okay, now actually I got to make sure that I'm down on the right function, so I had to use my up down arrow keys to get from function to function, and then I move to the left a little bit, press enter, move to the right a little bit, press enter, and I get this value right here. I'm not entirely sure what that is. I know that the minimum now is negative 6.125. I can quit. This is something I love about this calculator here. It's stored that in its memory. So if I press alpha and I go down to y, which is number 1, I get the y right here, and if I press enter, it remembered that that was negative 6.125. Choose your math button, and the very first option you get is to convert that to a fraction, and I get negative 49/8. So that value that I chose here was correct.
Let f of x equal x minus 3 and g of x equal x squared minus 8x plus 15. Determine h of x, which is f of x divided by g of x, and graph it to determine the following. And by the way, I made a mistake on this one. See if you can catch it before I do.
All right, so now in this case right here, we're going to put this all together as a division. So we know that h of x is going to equal, we've got f of x over g of x, so this will be x minus 3 over x squared minus 8x plus 15. Now I'm going to do a lot of this stuff just by hand here, just doing the algebra, and then maybe what we'll do is we'll use the calculator to confirm that. So the first thing I want to do here is factor, and I'm going to get x minus 3, x minus 5. Okay, I can cancel those x minus 3 so long as I state, so long as I include with my answer, because remember right now these are not equal to each other, because this one is undefined at 3, this one isn't. So as long as I state that x cannot equal negative 3, then now these are the same here. There is also another restriction here, x can't equal positive 5. It's not as necessary that I write that because I can see it right there. Now the domain of f of x, well, this was all reals. Okay, the range of f of x, this is going to be all reals. Now I can verify that by simply going to my calculator and entering, whoops, sorry, wrong button, x minus 3. That's just a straight line, okay? G of x is going to be x squared minus 8x plus 15. Oh, sorry, I don't know what I was thinking there. This is where we're supposed to put the range here. And it's a quadratic, and then so x is an element of the reals. Now, if I plug this in, I'm going to go down to y2 here. X squared minus 8x plus 15. I'm going to graph this guy here, see what it looks like. There it comes, there it comes, there it goes. Now, its domain is all reals. It's a quadratic. It's going to be defined for all values of x here. But its range isn't all reals. Okay, it's got a minimum. Now, right now, the calculator is on the wrong graph. I want it to be in the parabola, so I'm going to use the up-down keys to move from function to function. So move up. I'm going to come down here, and I want to find the minimum value, so I move to the left of the minimum, move to the right of the minimum, make sure the minimum is between those two lines, press enter to get past the guess. And my answer here is going to be the point 4 comma negative 1. Okay, which means my range here is going to be that y is greater than or equal to negative 1. Now, h of x does not have the same domain here. Okay, h of x, I've already dealt with it right here. H of x is going to be equivalent to this, but it's going to have this limitation here. X cannot equal negative 3 or positive 5. Now, additionally, look at the value here. It's going to have an asymptote. Okay, this thing here is going to have a horizontal asymptote when y is equal to 0. Okay, because when the denominator gets really, really large, this whole thing is going to go to 0. So it's going to have a vertical asymptote. Sorry, it's going to have a vertical asymptote someplace else here. It's going to have a horizontal asymptote at 0. So we can include in here y cannot equal 0. There is, however, another restriction here related to the point discontinuity. Okay, I'm sorry, not the 5. This is going to be the negative 3. And if I plug negative 3 into this, I get 1 over negative 3 minus 5, negative 8. So not only can it not equal the horizontal asymptote, I can't let it equal here negative 1/8 because that point goes with the point, sorry, that coordinate goes with the point discontinuity. So it's got a vertical asymptote here at x is equal to positive 5. That's my vertical asymptote, the essential discontinuity. And the point discontinuity we just found here was negative 3 comma negative 1/8. Now, let's plug this stuff in. We've just plugged in those two functions right here. So I'm going to go back to y equals. Come down to y3. I'm going to make this vars. Remember the vars button is right over here. Y vars function. We're going to make this y1 divided by vars. Go over to y vars function y2. So now my y3 here is going to be the quotient of those two, and press graph. Okay, and there we go. We seem to be, you can see right here. Now, the calculator has difficulty with the vertical line. That's why when it swoops up like this, when it gets very close to vertical, the calculator has a little bit of difficulty here. But you can see 1, 2, 3, 4, 5. Yeah, there it is. It's undefined here at 5. Now, I also know that it's undefined at 0 comma negative 1/8. Okay, or sorry, not negative 0 comma, negative 3 comma negative 1/8. Now, the calculator can actually show you that plot, that hole there, if we go second, sorry, not second, just go into zoom and go to zoom decimal. I'm not entirely sure this is going to work for this calculator right now, but zoom decimal. Oh my gosh, I have made a ridiculous mistake here, and I hope okay, actually, this is great. Okay, I hope everybody can see what's going on here. I made a little bit of a screw up here. And I'm going to go back and fix it, but I'm so glad this happened here. And if you've been following along, hopefully you caught it and you're like, what the heck? But whatever, don't bother writing little comments here, I caught it. Look at the graph right here, puts a little hole right here. Now this is not at negative 3, this is at positive 3. And notice the little hole there. If you use zoom decimal, the calculator is going to illustrate those point discontinuities. Now, I screwed this up. I made a little sign error, which is very easy to do here, apparently. Okay, when x minus 3 cancels with x minus 3, the restriction here is positive 3. Okay, now we come over here. If we plug positive 3 into this, it's going to be 1 over 3 minus 5. Well, that's negative 2. So this point should actually be 3 comma negative 1/2. Up here, this is going to be, for our range here, negative 1/2. Now, I probably should go back and fix that, but actually I love the fact that that happened, and I'm using the calculator to show me where I screwed up. And then I can go back and check really quickly what my error is. That's a great learning moment. Watch me screw up and learn from it.
Use the graphs of f of x and g of x to evaluate the following.
All right, so here's another one of those questions where we're going to piece together the operations based on the graph here. So again, we have to make sure we understand which one's f of x, which one's g of x. F of x is the dark line, g of x is the light parabola. So our first question is f times g at negative 1. So we go to negative 1, okay, right here. F is going to be negative 4, g is going to be positive 5. So this is going to be negative 4 times positive 5. The answer is negative 20. Good. Right here is going to be f divided by g of 1. Well, f of 1 is 2. G of 1, so we go down to 1 here. G of 1 is going to be negative 3. There's really not much we can do other than pull that negative out front and make that negative 2/3. Next one, g of over f of 0. Now this time g is in the numerator, so g at 0 looks like 0. Now it really doesn't matter what f is so long as f isn't 0. Okay? Doesn't matter what else it's going to be, but as long as it's not 0, then we're okay here. And it turns out f actually is negative 1. And so our answer is going to be 0. Now for any value of f other than 0, this would have been 0. G times f of 3, okay, well g at 3, here's 3. G at 3 looks to be negative 3. F of 3, okay, f of 3 right up there looks like 8. So negative 3 by 8 is going to be negative 24. So again, and I hope you're seeing the pattern here, I'm using my x coordinates, I'm going along that vertical line here, and I'm just picking the two y coordinates that correspond to the two functions and either multiplying or dividing them the way I'm told to.
Add the sketch of each combined function to the set of axes shown. H of x is equal to f of x multiplied by g of x.
Okay, so here we are. Once again, we're going to graph a combination of these functions based on their graphs here. So, and what I've got here is I've got f times g, so we're going to multiply these two together. Now before I even get to that spot right there, I'm noticing that I've got f is a linear function, g is a linear function. I can guess pretty comfortably that if I've got a linear by a linear, I'm going to get a quadratic. I'm expecting that I'm going to get a parabola as a result here, a quadratic. Now, we just pick an x coordinate and we go down. I'm going to choose negative 4 here. We go down. We're going to multiply the y coordinate here, negative 3, by the y coordinate here, negative 6. Well, negative 3 times negative 6 is going to be positive 18. Okay, that's off the grid. That's too much here. So let's pull this in a little bit. If we go to negative 2, my y coordinate is negative 2. My y coordinate here is negative 4. So if I multiply negative 2 by negative 4, I'm going to get positive 8. Well, that's off too. Now, not by a ton. It's actually going to be up there. Well, this is not great here. Okay, let's go to 0. Let's go to where x is equal to 0. This is going to be negative 1 by negative 2. That's going to be positive 2 when I put those together. There we go. So there's a point right there. And I'll make that nice and big so we can see it. This one up here, nice and big. Move over. Okay, they're both equal to 0 here. Their product is going to be 0. That point is going to stay right there. Awesome. Now let's move over. The y coordinate here is 1. The y coordinate here is 2. When you multiply those together, we're going to get 2. And over a little bit further here, the y-coordinate 6 is going to be 2. Y-coordinate here is going to be 4. So together that's 8. Now that's going to mirror this one over here, which I drew off the grid here. So now putting those together, kind of see that I'm going to get this as my quadratic. So this graph right here, this is my h of x.
S of x is equal to f of x divided by g of x.
Okay, so now for this one, I'm going to take these two functions that I'm given right here, and I'm going to graph their quotient. So now it's important in this case here to recognize which one of these things is the numerator, which one's the denominator here. Now this is going to show us a couple things here. I'm going to kind of be lazy about this because I know at this point, because of previous lessons here, I know what a rational function should look like. Okay, particularly when I've got function over function. And if I've got a linear over a linear, it should be relatively straightforward here. Now I'll feed in some of the extra data points here in just a moment here, but for example, g of x is in the denominator. When g of x hits 0, okay, that is going to produce a non-permissible, which is going to end up being an essential discontinuity here. So right there, at x equals positive 1, I'm going to end up with a vertical asymptote. Okay. Now, when f of x hold on a second. Yeah, I'm sorry. That's what I had a little brain fart there, but that's what I meant to say there. When my f of x goes to 0, that's going to end up being the x-intercept of the function here, okay? Because the numerator is going to determine where this thing goes to 0, so it's going to go to 0 right there. So right here is my vertical asymptote, right here is my x-intercept. Now what I'm going to do is I'm going to go through and just start to divide some of these values here. So we come along here, and I really can't go that far here. This is f of x, negative 2 is the y-coordinate here, negative 2, now go up to g of x, divided by 6. Well, negative 2 divided by 6 is going to be negative 1/3. Okay, negative 2 divided by 6 is going to be negative 1, so it's going to be like right there. Well, that's kind of interesting. Now, over here on the other side here, and I can't go very far here because I don't have much of g of x here. When x is equal to 2, f is going to be 2, g is going to be negative 2, so that's going to be 1. When x is 3, okay, when x is 3, f is going to be 3, g is going to be negative 4. Oh, hold it, did I screw up that other one here? I'm so sorry there. Yes, I did. Yes, I did. Because it's going to be negative, okay? Obviously, it's going to be negative here. When f is positive 2 and g is negative 2, it's going to be negative 1. Now, down here, when f is, when x is 3, f is going to be positive 3, g here is negative 4, so it's going to be negative 3/4. It's going to go down here. And we can go one step further here at 4 here. At 4, f is going to be positive 4. It's going to be negative 6. This is going to be negative 2/3. So there we go. So the graph must actually look something like this. And actually, it's got to look something like this, which means I must be getting a horizontal asymptote somewhere tucked really tightly inside there. Okay. Now, I could figure out what that is based on these two values here. And actually, maybe I should, because I can do this here. I know, for example, that f of x has got a slope of 1 and a y-intercept of 0. So that is the entire. That is right there the entire function f of x. G of x has a slope of negative 2 and a y-intercept of 2. So I can actually write that out here, and even from there, I can tell you that my horizontal asymptote is going to be y is equal to negative 1/2, and that actually bears itself out in the little bit of work I did. I didn't know exactly what it was going to be, but I certainly knew it was going to be somewhere in that neighborhood.
Evaluate each combined function using f of x equal to x squared plus 1 and g of x is equal to negative 2x. F times g of x evaluated at 5.
All right. So we're back down to questions like this where we're going to evaluate the product of two functions at a given value. We'll take a look at a couple of different ways of doing this. First of all, notice that f of x is going to be x squared plus 1, and g of x is going to be negative 2x. So remember, that dot there means the product between those two. So now we're going to distribute that negative 2x through. So we're going to get negative 2x cubed minus 2x. Okay? And now if I evaluate this at 5, I'm going to get, okay, what do we got here? Well, I should do it like this. 5 cubed is going to be 125. Okay, times negative 2. Okay, that's going to be negative 250. And then minus 2 times 5. Well, 2 times 5 is 10 here. So this is going to be negative 260. Okay? The other way of doing this is, because we're multiplying f and g together here, we can do f times g at 5 is going to be f at 5 times g at 5. You can do this in a slightly different order, and you might find this a fair bit easier. And I'm going to actually just do it really quickly like this here. F at 5 is going to be 5 squared, or 25 plus 1, 26, times, well, negative 2 times 5, which will be negative 10. And there it is. There's our negative 2. Whoops, daisies, that doesn't look nice at all. Get in there. There is my negative 260 that I got in the previous little bit of work.
F divided by g evaluated at negative 2.
Okay, in this case right here, we're looking at division. So let's come up with the expression here first. So first of all, we'll do f of x over g of x. So x squared plus 1 over negative 2 of x. Sorry, negative, not 2 of x, just negative 2x here. And we'll evaluate this at negative 2. Actually, that's a terrible notation. I shouldn't have done that. We're just going to evaluate this at negative 2. It would probably makes more sense for me to write this like this. Put a little square bracket here, x equals negative 2. And I will plug that in here. Negative 2 squared is going to be 4 plus 1 is 5. Negative 2 times negative 2 is going to be 4. So the answer here is 5 fourths. The other way of doing this is to make this f of negative 2 divided by g of negative 2. Well, f of negative 2 is going to be, well, 5. And g of negative 2, again, is going to be 4. Actually, in this particular case here, because there was no simplifying that I really could do in this expression right here, these are basically just two ways of looking at the exact same thing.
G divided by f evaluated at 2.
All right, so this question is really, really similar to the one that we just did. So this time we're going to put g of x in the numerator and f of x in the denominator. I'm going to evaluate this when x is equal to positive 2 this time. Positive 2. So negative 2 times positive 2 is going to be negative 4. And then positive 2 squared plus 1 is 5. So the answer here is negative 4 fifths. And again, if we evaluate this, g of positive 2 divided by f of positive 2, g of positive 2, negative 2 times positive 2, again, negative 4. And then f of positive 2, 2 squared plus 1 is 5. Similar sort of thing to the one we did before. There wasn't a lot of simplifying, so really, this is just two different ways of looking at the exact same work.
If h of x is equal to f of x divided by g of x, and f of x is equal to 2x minus 5, what is g of x for each of the combined functions below? H of x equals 2x minus 5 divided by x plus 3.
All right, so now we're going to do some manipulation with the expressions here. And again, it's wonderful how closely this would match your intuition on these sorts of problems here. So if h of x is f over g, and we know what f is, how do we get g? Well, if h is f divided by g, I could do this a couple of different ways, but you might think of it as multiplying, first of all, by g, both sides by g, canceling on the right-hand side, and then divide by h. So g is going to equal f divided by h. Now, let's go through and do that. So g is going to equal f, 2x minus 5, divided by, now in this case, h, we get from here 2x minus 5 over x plus 3. So the resulting expression here is actually a complex fraction, I've got a fraction divided by a fraction. So what I'm going to do here is multiply by the reciprocal of the denominator, or the divisor I should say. Notice that the 2x minus 5s are going to cancel with each other. And what I'm going to be left with is x plus 3. Now, that's great. That's great. Remember, these are not exactly the same. As soon as I canceled that out here, I got rid of a non-permissible, basically the hole in the graph here. So I have to make sure I state to make these things equal, because right now they're just equivalent. But to make them equal, I have to say that x can't equal 5 halves. And now this expression is going to be equal to this one right here. Okay. Now, there was another restriction that came up, and you should remember this from a previous course here. Notice that h of x was undefined at -3. That is also a restriction that I need to state, because that has an impact on the overall answer here. This x plus 3, you're not seeing any restrictions here whatsoever, and g, it would carry that restriction through with it right here, even though we're moving it to a different position. Originally, it's in the denominator of one of my factors, and I have to deal with that.
h of x equals 1 divided by x plus 6.
Okay, so here's another one here. It's basically similar question to one we just did here. So again, I should be able to write that g is equal to f divided by h. Okay, now I know what f is in this case. I know that f is going to be 2x minus 5. So this means I'm going to get 2x minus 5 divided by, and h in this case is 1 over x plus 6. Okay, now in order to get g here, what I got to do is I'm dividing by this fraction. So what I'm going to do is multiply by the reciprocal of the divisor. So that'll be x plus 6. And now I should really just multiply that out here. I'll get 2x squared plus 12 minus 5 is plus 7 minus 30. And that's true so long as I identify the restriction here that x cannot equal -6. If x equals -6, that divisor becomes undefined. Okay, I don't see that in this expression. In this right here, there are no non-permissibles. But because there was one in the original expression here, I have to state it in order to make sure that those remain equal there. Now, just before we go, someone's going to say, wait a minute, for this previous one here, if I already knew that f of x was 2x minus 5, couldn't I just have said that xg was equal to x plus 3? Yeah, you could have. But where was the fun in that? This was way more fun than just identifying those restrictions right away. The other issue that you'd get with something like that is you wouldn't see this non-permissible popping up here, this this x can't equal 5 halves that you get when you do it like this.
Given the functions f of x equals 3x squared minus 11x plus 6, and g of x is equal to x squared minus 9, find the following.
Okay, there's a bunch that they want us to do here. So we've got the functions for f and g here. We want to determine a simplified expression for f divided by g. Okay, so h of x is going to be equal to f, 3x squared minus 11x plus 6, divided by x squared minus 9. Now, this is going to be equivalent to, let's factor this. The denominator is going to factor pretty easy because that's just a difference of squares. So x minus 3, x plus 3. My numerator here has got to be 3x and x. And then what have I got here? Factors of 6 will be 3 and 2. I can't put the 3 here because then there'd be a common factor. So 3's got to go here. 2's got to go here. So that's going to give me 9 and 2 as my outer and my inner products here. And I can get that negative 11 if these are both negative. So now, these two can be canceled, and I'll be left with 3x minus 2 over x plus 3. Now, that's not equal yet. They're equivalent. Okay? They're equivalent to each other. They don't become equal until I state that x can't equal positive 3, the value that I just, okay, and that comes from the factor that I just canceled here. As soon as I write that, though, now I can write that they are equal to each other. Okay? So now, we're going to sketch the graph of h of x here. Okay, well, we know that this thing is going to be undefined at -3. That's going to be an essential discontinuity of vertical asymptote. Okay? Additionally, I know based on previous work here that if I ignore everything else and just look at the leading terms here, I'm going to get a horizontal asymptote y equals 3. Okay, I hope that's clear. I'll try to make that a little darker there. I also know that this thing is going to have a point discontinuity, okay, when x is equal to -3. I'm sorry, not -3, +3. It's undefined at -3. It's going to have that's the second time I've done that. Going to be point discontinuity at 3. And if I plug 3 in, I'm going to get 6 minus 2 is 4. 3 plus 3 is 6. So 4/6 or 2/3. So it's going to have this point discontinuity at 3, comma, 2/3. It's going to have a big dot there. Other things I can find out. I know that I'm going to have an x-intercept here, when this goes to 0, of positive 2/3. So 2/3 is going to go through right there. I know that's going to have a y-intercept of negative 2/3. Now there's a whole lot of this 2/3 stuff going on here. That's kind of crazy. Now, so this part right here, we're going to be approaching the asymptote. It's got to look something like this. And then it's going to keep going up towards that value right here. Now, just for fun, what I might do here is plug in, for example, a -5 and see what that gets me here. So -5, 3 times -5 is going to be -15 minus 2 is going to be -17. And then -5 plus 3 will be -2. And it'll be 8.5. So that's going to give me somewhere up here. So you can kind of get a little piece of the graph up here. It's going to look something like that. Okay, all I did was I just wanted to have kind of a sense of where that graph was located. That's why I just quickly threw in the -5 in there. But there you go. State the domain and range of h of x here. Well, I know for my domain, I know that x cannot equal -3. That's my vertical asymptote. It also can't equal +3. That's my point discontinuity. My range is going to be such that y can't equal +3. Okay, that's my horizontal asymptote. It also can't equal 2/3 because that's the point discontinuity. So there we go. So this is a nice link to material that we did previously in this chapter.
Use the graph below to evaluate the following.
All right, we got a nice big graph here to work with. So we've got f times g at -4. Okay, so we're going to come down here to -4. We've got to make sure we know which function is which here. So f is the dotted one, g is the solid one here. At -4, okay, at -4, f is -6. G, oh, and this is right on the edge of g here. This is going to be 2. So the answer here is going to be -12. Okay, good. Any further to the left, and this would have not worked for anything. F times g of 12. Okay, so f, let's take a look at this. F at 12. All right, 12 is right here. F at 12. Ooh, that's like running right off the edge of the graph here. That looks to be 10. G at 12. Okay, well, G at 12 is right here. G at 12 looks to be 6. And so the product of those two is going to be 60. Now we're going to do some division here. Take a look at what's in the numerator here. It's f at 5. So f at 5 here is going to be 3. I know it's pretty small there. F at 5 is going to be 3. Try to make that a little bit bigger so that you're not squinting to see that. 3, hopefully that's a bit bigger. G at 5, okay, G is a solid here. G at 5 is going to be, looks like 5 here. That's about the best I can do. 3/5. I could say 0.6. Whatever, not necessary. Again, F is in the numerator for this last one. F at 0 is -2. G at 0 is 4. Okay, I can do a little bit of simplifying here. That's going to become -1/2. Again, all I'm doing is I'm using these x coordinates. That becomes a vertical line. I pick the y coordinates off, and I'm either going to multiply those or divide them in the correct order.
If h of x is equal to f times g of x, where h of x is equal to 3x cubed plus 17x squared plus 9x minus 5, and f of x is x plus 5, what is g of x?
All right, well, as before here, I can manipulate these expressions here just the way I could if they were variables here. So h is equal to f times g, that's what that's telling me, and I'm looking for g. Well, I can see here I can divide both sides by f here, so g is going to equal h over f. Okay, so I have to divide this expression for h by this expression for f. Now, look, because I'm dividing by x plus 5, I can use synthetic division here. And I'm going to, because it's the kind of a cheap, easy way out of this problem. So I'm going to put negative 5 outside my box, and I'm going to start grabbing my coefficients here. 3, 17, 9, negative 5. Cubic, quadratic, linear, constant. Good. Bring down the 3. Negative 5 times 3 is going to be negative 15. I add them to get 2. Negative 5 times 2 is going to be negative 10. I add those to get negative 1. Negative 5 times negative 1 is positive 5. I add those to get 0. There's my remainder. So my remainder is 0. What I'm left with here is my quotient, and in this case, more specifically, this is my g of x. Okay, so it's just a matter of interpretation. That negative 1, reading this way, this is my remainder here. This is my constant. Okay, this is my linear term, and out here, this will be my quadratic term. So 3x squared plus 2x minus 1. That's the g that I'm looking for.
Let f of x equal x plus 2 and g of x be x squared plus 8x plus 12. If h of x is equal to f over g of x, complete the following information below.
Okay, so with this question here, we've already done several questions kind of like this here. We're just going one more time here. We're creating a quotient here. So h of x, as we've already seen in this function here, is f over g. F was x plus 2, and g was x squared plus 8x plus 12. Now, to simplify this, what I need to do here is factor first. So x plus 2 divided by, okay, well my denominator is going to factor down to x plus 2, x plus 6. All right, that can be simplified by simply canceling the x plus 2's out, but again, that doesn't make it equal to, it only makes it equivalent to 1 over x plus 6. Because there is one value where these two are not equal. They are not the same at negative 2. So I have to actually state here x can't equal negative 2. And when I do that, then I make these two equal to each other. So now carrying this up to here, the equation of h of x is going to equal 1 over x plus 6, so long as x does not equal negative 2. So what's the domain of h of x? Okay, well, a couple of things here. First of all, x cannot equal negative 2. I had to state that because it was the restriction that I canceled out. Now it's gone, so I have to state it to make those equal. But the other one is going to be x can't equal negative 6. I get that from the resulting expression. I can't do anything about it. It's stuck in the denominator. Boom. The range. Okay, the range here. Now let's take a quick look at this function here. If you compare the highest degree terms, I'm going to get x divided by x squared. I can cancel the x, 1 over x. And as x gets large, this is going to go to 0. So I'm going to have a horizontal asymptote there at 0. And I might as well just do this right now. Y is equal to 0. Okay, and actually I could probably state the vertical asymptote here. X is equal to negative 6 because I've already done that work here. So my range is going to be, though, y cannot equal 0. But because of this negative 2 here that I have to state, I know that there's a point discontinuity. If I plug negative 2 into my simplified formula, 1 over negative 2 plus 6, well, negative 2 plus 6 is 4. So there's going to be an issue at 1/4. So my point discontinuity is going to be negative 2, positive 1/4, which means my range is y cannot equal 1/4. Now, with all of that information, I should be able to come up with a fairly reasonable graph here. Okay, so first of all, I'm going to have a vertical asymptote at negative 6. Just draw that in. I am going to have a horizontal asymptote, okay, on the x-axis. This is y equals 0. Try to make that a little bit more visible. It's a little tough when that line is already there and fairly dark here. But anyway, there you go. Okay, it's got a point discontinuity at -2 1/4. So -2 1/4, and that's like right there. Okay, now a couple other things here. Notice I'm not going to get an x-intercept here, but I can get a y-intercept here of 1/6. It's going to drop down like this. Essentially what's got to happen now is, in order for this to work here, it's got to approach that asymptote. It goes through, hits that point discontinuity, and approaches the line there. Which means the other part of this graph's got to be over here, approaching those two asymptotes like that. Okay? That's roughly what this graph has got to look like.